Hello and welcome back. Today on the bench we've got the big green amp, which you've seen previously. I'm not really going to get into detail about the big green amp today. What I wanted to talk about, which will hopefully help a few of you out who are only just sort of starting on this sort of odyssey, is amplifier testing. So first off, why do we want to test an amplifier and what test can we do? Well, first and foremost, we test amplifiers to find faults in a lot of cases. Either it could be an amplifier that you've been asked to repair or one you've built. Either way, we've got to find out if it's got any faults, what the faults are. When we know what the faults are, we can then address them and hopefully fix them. This applies both to valve amplifiers and to transistor amplifiers. With transistor amplifiers though, we test for things like DC on the outputs, which you don't want DC because it will knacker your speakers up. And then the other thing some transistor amplifiers suffer with is really high frequency oscillation. For instance, I had a H&H 500 S500D amplifier and that worked fine, but when I actually tested it at about 100 kilohertz, it was oscillating like mad. You just wouldn't hear that over speakers, but it's a fault and it wanted curing. The other things we want to test for are total harmonic distortion. What's total harmonic distortion? And all an amplifier should do is take the signal that we put in, amplify it, in other words make it bigger, but without adding any distortion or any other things. It should be basically what you put in, you should get out. So in other words, a straight wire with gain. Most amplifiers, however, do colour the sound. And with valve amplifiers, you want, well I particularly do, want the amplifier to colour the sound a bit. That's why we build valve amps. We don't really build them for ultra low total harmonic distortion. The other thing we want to check for is hum and noise. So when you turn the amplifier on, before you even put a music signal in, if you've got real high buzzing at the speakers, then you know it's not good. Another thing we want to test for is output power. So how much does the amplifier amplify the signal when it goes in? How much bigger is it when it comes out the other end? And the other thing we want to test for is input sensitivity, which sort of goes hand in hand with the output power. So how much signal do we need to put in so that the amplifier amplifies to its specified maximum output power? So it's no good putting something like 10 millivolts in on an amplifier like this, because although it will amplify it, we will never get 20 watts out. No way. So we need to know what is the input sensitivity. We'll go into details later. One last one, although this isn't by all means an exhaustive list, is intermodulation distortion. Because music is made up of lots of different frequencies, how do those different frequencies interact when they go through the amplifier? They shouldn't interact much, but they do. It's not really a test I do a lot. In fact, I can probably only remember doing it once. Right, another thing we test for is frequency response. So how good is it at amplifying low frequency signals, in other words how much bass has it got, and high frequency signals. And one last one is stability. Some amplifiers you will connect them to one set of speakers and the amplifier will work fine. Other times you will connect another type of speaker and it will start oscillating, self-oscillating. It just doesn't like those speakers. When I build my amplifiers, I try to build them so that they are stable with all loads. In other words, unconditionally stable. Another thing you want to test for is low frequency stability. So some amplifiers do what is called motorboating. So it's very low frequency oscillation. I have covered this in previous videos. In fact, I had this problem with this amplifier. Right, so we've got that out of the way, what we need to test amplifiers for. How do we test amplifiers? Traditionally you use something like this advanced signal generator, which produces sine waves from 20 Hz, and I think this one goes up to 200 kilohertz. You use something like this to put a signal in to the amplifier and see what comes out the other end. If you haven't got a signal generator, you can also use something like a phone, record a signal onto there. However, there's a caveat with that. Some other things you can test an amplifier with are, there are several PC based free software that you can use which have the signal generator in, and you can test for frequency, etc. Some of these well-known ones are REW, which is specifically used for testing speakers, but it can be used to test amplifiers. ARTA, A-R-T-A, Audacity to a point, which is more a recording. It's more a DAW, digital audio workstation. Or the one I use a lot is sound card scope, which is a lot simpler to use than REW and ARTA. I'll show you that in a minute on the PC. So you also need, if you're going to test using a PC, you will need a decent sound card. Although on some PCs you could use the sound card fitted to the PC, but usually they're not particularly very good. So you can use like a separate sound card. In my case I'm using a very mucky old sound blaster. I can't remember who made these. Yeah. So there you go. Line in, front, rear, speakers, SPDIF out, DIN, USB, microphones. Yep, this does the job. And we're basically just connecting that to the PC with a USB cable, and I'll show you what else you would need. If you can afford one, these are used by a lot of blokes, tend to be blokes, there are some women. These tend to be used by a lot of us, which is a HP 8903B audio analyzer. These are pretty much industry standard, although they are old. They're obviously more newer, up to date, all singing, all dancing analyzers, but this one does the job. Basically all it does is produce a very low very low distortion sine wave, and just test it. You stick it in, it will tell you how big the signal is that you are measuring, distortion, etc. Another thing that isn't essential, but I think it is really, if you want to test amplifiers to any great degree, you will need an oscilloscope. You can do a lot with an oscilloscope. In theory, if you know what you're doing, you can estimate total harmonic distortion and things of that nature. You can test frequency response on an oscilloscope. But yeah, an oscilloscope is pretty essential. Finding an oscilloscope is a whole can of worms. This is obviously a very old oscilloscope, probably made in the 1960s, so they are a challenge to keep running, as you have seen from some of my videos. But you can pick up a lot smaller, simpler analog scopes, or you can get a sort of new digital one, although I know bugger all about that. However, some of those bits of software that I mentioned have an oscilloscope in them. Going back to signal generators, this being a simple one, although it's got a few more functions on it than a lot of more simple ones don't have, but it's pretty simple. You've got a big knob here, and that changes your frequency. this knob here will set the range. So if we click it over to A, and if we look at this what do you call it, chart here, that's band A. So as you can see, that goes from 15 Hertz all the way up to 300. To go higher, you click the knob up there and again adjust it there. All these knobs here these are just attenuators, so they just reduce or make bigger the signal that's coming out of these terminals here. On the HB8903B, as you will see, have you seen me done before, you just basically punch it in on these keys here. Well, let's have a look at so what I've got here, this is an old, so what I've got here, this is an old PC, it's running Windows XP. So this is sound card scope. As you can see, we've got a oscilloscope, but with a lot of these PC based oscilloscopes and audio testing software, you are limited by the sound card limit, which usually are about 20 Hertz to 20 kilohertz. You can't go much higher than that. So as you can see, we've got a scope with the normal sort of controls, XY graph, frequency, which is basically FFT, a signal generator. We'll just go back to the frequency in the oscilloscope. As you can see here, we've got a total harmonic distortion reading. I found when using this in the past that it agrees completely with my HB8903B, so it will test to the same accuracy and degree that the 8903B can, to a point. So it's a pretty good simple bit of software, and there's not a lot of setting up you need to do either. It just works pretty well. I won't get into R2 and REW. There's plenty of better guides on YouTube for that will deal with those specifically. But all we want to do really is just test frequency, THD, total harmonic distortion, and that's about it really. That's all I use it for. I just use this FFT to look to see the harmonics that an amplifier is producing. The last bit of kit you need really is a dummy load. As you can see, mine is quite big and it can test up to quite high wattages, quite high power. This is not just, basically all this is inside here is a big heatsink with a load of resistors. Those are big, these type of resistors, 50 watt ones. So in there are 8 2 ohm 50 watt resistors. I can only test 8 ohms on this, but that's what I use mostly, as most of the work I do is on valve amplifiers. You could also just use this sort of resistor here. I use this to test for 4 ohms. This can be altered by moving this ring here, this terminal here. You could, in theory, just use a resistor like this, or not this particular one, and stick it in a cup of water. Only do that for AC though, and it's not really a good idea to have a cup of water sitting right next to electronics, but you can, in theory, do that. Incorporated into this dummy load is the ability to connect to speakers, which I just do with these jumping links. I prefer to use these rather than relays because there's a lot of current going through these things, and I found switches and relays just can't handle the current. There are quite a few designs and videos out there on dummy loads, but like I say, essentially this is just 4 big resistors all connected together in series to give 8 ohms and 8 ohms, so it's stereo. But more important for when you are testing with a PC is some sort of attenuator, and that just means you've got a couple of high value resistors in parallel with that dummy load, so that you're not putting 20 odd volts into your sound card, because that will make it very unhappy and smoke a lot. Not a good idea. I think in this case I use something like a 10k and a 1k, something like that. You don't want anything too low, obviously, because it will affect the 8R. Another thing that's often mentioned with dummy loads and what resistors you use is using non-inductive resistors. I think this is silly, to be honest. If you look at these resistors, these are basically got a big bit of graphite, and it's got like a helical sort of scratch, what do you call it, helical thingy-doo-dah around it. The amount of inductance that one of these has is really tiny. I bet you couldn't even, you'd struggle to measure it, to be honest. And so let's just say it's something like 400 millihenries or something crazy like that. Well, that's only going to affect really high frequency measurements. So I wouldn't worry about getting non-inductive resistors. It really isn't important, I don't think. I think people make too much of it. But there we go. So yeah, all you need is a heatsink, some resistors, and there you go. And some sort of attenuator. As you can see, I've got like a little precision 1k pot here so that I can vary it if I want to, but I very rarely use that. The other thing I've got connected to the dummy loads are these BNC connectors. However, there's a trap there, because most amplifiers use the ground as common for both speakers, some don't. So for that I've got an earth lift. Basically all these BNC connectors the grounds are connected to them, regardless of what your dummy load resistors are doing. And effectively they are connected to mains earth through the oscilloscope, unless you lift the earth on your oscilloscope, which isn't advised. So I've just got a earth lift thing there, which just basically disconnects those from one side to the other, but essentially they are joined if I connect them to an oscilloscope. That's a trap that you can fall into, and I have fallen into it. Okay, let's do some testing after all that waffle. First test we're going to do is output power, to see how many watts we're getting out of this thing. So obviously we need to turn the thing on first and let it warm up. Because this is a valve amplifier, you should never power a valve amplifier up without a load connected. The other thing I didn't go into was why we use dummy loads rather than a speaker. If we used a speaker, first things first, the speaker has a nominal impedance of 8 ohms. However, when the frequency changes, that impedance will change from 8 ohms to maybe 40 ohms to maybe 4 ohms. So as the frequency changes, the speaker will react. It's not a linear device. A resistor is a linear device, so it will test the same at 1 kilohertz, 100 hertz, or 100 kilohertz. So that's why we use dummy load resistors. Another reason is you don't want to connect a potentially faulty amplifier to your best set of speakers. So we use a dummy load. However, I do use a sort of clip-on speaker that I can just, you know, it's an old car speaker, it doesn't matter what happens to it, I don't care if it blows up. So I sometimes use that because it's good to listen to an amplifier. And we'll get into listening as well. There's so much to cover on this subject, so basically I want to try and give a broad overview here. Our amplifier's on. I've set the HB8903B to 1 kHz with 500 millivolts input. Let's talk about input voltages. Your basic consumer line level standard is minus 10 dBV with a big V. What does that mean? Without going into loads and loads and loads of what a dB is and all that, in terms of AC RMS it is 316 millivolts RMS. However, some CD players can kick out 2 volts RMS. What's RMS? I think you best look that one up yourself, or we're going to be here all day. So I usually start off something like 500 millivolts, and this is going into the potentiometer. I wouldn't put 500 millivolts straight into the first stage. Let's click our oscilloscope on, because it's always nice to see what's happening to the waveform, and it's pretty essential when we're testing for output power. You need to test what the output power is before it clips. What does clipping means? It just means that the amplifier can't put out any more voltage, so it starts to have hissy fits. Basically the waveform starts to flatten off at the top. It just hasn't got any more oomph. Right, there's our oscilloscope on. I hope you can see that. So there we've got a waveform there, and we are measuring 1.1 volt RMS. So now I've got to reduce the voltage, I've got to attenuate the signal going into the oscilloscope basically. Keep turning that up until it just starts to clip. As you can see, we're getting a bit of peak in here. We've got 10 volts. Point you there. You see that there, 10 volts RMS. You're back to the oscilloscope. Right, see there, it's starting to flatten off. It's just run out of oomph. So we just reduce that a little, and we are getting 12.97. Let's call that 13 volts. You don't want to be powering your amplifier up at full output for long periods of time. It's not good for it, although it's a useful indication of how it will behave. We've now got a figure which we can use to calculate our output, maximum output power of the amplifier. So we will say 13 volts RMS. So we just square that or times it by itself. So 13 times 13, and then we've got to divide that by our load or speaker impedance, dummy load impedance, whichever. Although dummy load, as mentioned previously, is more linear than a speaker. So let's plug those figures in. 13 times 13, you probably can't see this, equals 169 divided by 8 is 21.125. 21, call it 21 watts. So that's our output power calculated. You could do this at different frequencies if you want. Do you want to do that? Let's go mad. Let's test it at different frequencies. So I've set the HB8903B, signal generator to 100 Hz, still at 500 millivolts output. Turning up the amplifier volume control. Right, you see that was starting to clip there, and we have a figure of 13 still, which is pretty damn good. I was expecting that to be less, and it's not that down, so we still got 13. Right, let's change that to 10 kilohertz. We'll have to change our time based on our oscilloscope. Turn it up. I hope you can see this. As I turn that up, we are starting to get some sort of distortion here. And if you notice that the bottom of the waveform sort of pinched off, so we've got like a artifact here and there. Mind you, we are at 15 volts. If I'll set it to 13 ish, so that's a good waveform, 13.33. But as you saw, we were getting more output power. It was about 15 volts RMS at 10 kilohertz. Let's just change that to 20 kilohertz. And as you can see, that has dropped right down. It's half in numbers. We were at 13, roughly half, a bit more than half. And as you can see from our oscilloscope screen, you can see it's physically smaller. So that's giving you a rough indication of the frequency response of the amplifier. Whilst testing there, I noticed an anomaly with the oscilloscope. So as you can see there, we've got 4.5 volts RMS, and that is showing that on the screen okay. Right, now if you look, that's showing that that is clipping. That's not the amplifier that's clipping, this is the oscilloscope. So I suspect I've got some sort of problem with the oscilloscope vertical amplifier plug-in. You get this sometimes, you find that you get odd results, and you have to try and dig into it a bit to find out whether it is the amplifier that you're testing or the test gear that is the issue or the fault. Anyway, let's get back to testing. But it is something that's worthwhile pointing out. Watch your bloody test gear. If it's giving you funny results, or if the amplifier is testing funny, check your test gear. Okay, so going back a little ways and looking for faults. When testing this amplifier the other day, I did notice a few. So we've got our volume controls here, left, right. Just turn that one up, so we'll turn that there and there, so that the volume controls are sitting in the same position roughly. So we're getting 2 volts on the right channel roughly. Oh sorry, 2 volts on the left channel roughly. But we're getting 4 volts on the right channel. So I'll do that using the oscilloscope. Right channel, left channel. So we found a fault. It's not a fault as such, but it's an anomaly. If you also look, our VU meters aren't telling the same story. Although our volume pots are set to roughly the same position, we've got a difference, a disparity in the VU meters. So we've found a fault already. If you look online, there are quite a few big PDFs, free PDFs, that cover this subject in far more detail. One of which is worth looking at, which is Audio Measuring Handbook by Bob Metzler. And then there is the Tektronix Cookbook of Standard Audio Tests. Although the latter is an accompaniment to a Tektronix spectrum analyzer, a lot of the principles and calculations still remain valid. Okay, so in the next one we will cover hum and noise, input sensitivity, total harmonic distortion, and lots of other fun stuff. I hope this helps in some way. Please don't take this as the gospel of audio amplifier testing. Research it for yourselves. This is just what I've picked up and learned in the last 10 years. This is just a broad overview of the subject. Well, thanks for sticking through this. Thank you all for watching. Take care of yourselves. Ta-da for now.